Okay, chapter 6, section 2. So last section, we talk about the integrals, right? Anti-differentiation. And we use this elongated s, right, with dx, which means cut x-axis into infinite many pieces, right? Each piece we call dot x. But then in the infinite world, it becomes dx. And then this is in the infinite world, it means some summation of this little x multiplied by, whatever this is. In the integral, this has a name called integrand. Right? Usually in the finite world, we have this summation sign, right? Or summarize something. Or then we could multiply by something. So that's a finite many. But we extend it to, we take a limit of this, right? Then we run to infinity, so we get this notation. We get this notation called integrals. Basically sum up some areas because we have 2 dimensions. But this is the second dimension. The 1 dimension is this pair, cutting x-axis into infinitely many pieces. Then each piece multiplied by the function, right? The function value. So then this we do not know, this has no intervals. So in this section, we're going to talk about the definite integral, which means we're going to talk about from one value of x, or maybe a, to another value of x. So this is the x-axis. And we want to sum up, we want to find the area of this. Because 2 dimension represents the area. We want to find the area of this. So we call this lower limit. So we put this a, so this is the interval, right? From a to b is an interval. We'll put the first number a into the lower limit, called the lower limit. We put the b in the upper limit. So this is called a definite integral. So remember, let's see one example we know, right? Let's see, we have 2x dx. So in this case, f of x is equals to 2x. And we want to anti-differentiate this. We want to find f of x, or maybe evaluate. So what do we have? Remember we said we add 1 to the exponent, we divide it by the new exponent. Then we add c to it. Right? So this will simplify, we just get x squared plus c. And we call this some f of x. It's not one function, but one family of functions. Because it depends on the initial value, we have different c's. So this is without the lower limit and upper limit. Now let's see, we give the lower limit, upper limit a value. Right? We see, okay, the lower limit is 0, the upper limit is 1 maybe, right? So those lower limit, upper limit could be any number. And then when we differentiate, when we anti-differentiate, we get x squared plus c. Then we want to evaluate from 0 to 1. Which means, so to evaluate at 1, we have 1 squared plus c, right? To evaluate at 0, we have 0 squared plus c. So 1 plus c minus c, that's just 1. So you see from here, we see c doesn't even play anything, contribute anything. So c doesn't contribute anything. So we have this one, we're going to write as, this. So once we recover to the original function, we just evaluate at a, So f of a b, right? The upper limit, which is 1 in this case, subtract f of a, in this case, is equals to 0. So that's definitely integral. So we do one step further than the indefinite integral. Indefinite integral means we do not specify the lower limit and the upper limit. And once we anti-differentiate, we get a family of functions. But a definite integral, we get a value because c does not matter in this case anymore. We just anti-differentiate the function, then we subtract. So we evaluate at the upper limit, we evaluate at the lower limit, then we subtract them. So that's a definite integral. Let's see some more examples. So that's this. So f prime of x equals to lowercase f of x. So this is a derivative of such f. So we just get f of b, we evaluate the capital letter f at b, at a, and we subtract them. So the number of this is called the net change of the function. Doesn't really matter of the name, all right? Let's see this example. We want to anti-differentiate x. All right, let's do that. X raised by 1, we plus 1 to it. We divide by 1 plus 1. Then we want to evaluate at 1, at 2. So that's x squared, right? So we get a 2 squared, we evaluate at 2. 2 squared divided by 2. X squared divided by 2. So this simplifies to be x squared divided by 2. We evaluate at 2, we have 2 squared divided by 2. Then subtract 1 squared divided by 2. So 2 squared is 4. 4 minus 1, which is 3. So we get 3 halves. Right? So we anti-differentiate, we evaluate at the upper limit, at the lower limit, we subtract them. So this picture is showing what's going on there, right? So f of b minus f of a. So each one in between, that's the net change. Let's see this example. We have e to the negative t. When we anti-differentiate, right? Negative t, in front of t is a negative 1. So m equals negative 1. We divide by negative 1. Then we evaluate at negative 1, at 1. So this is just a negative e to the negative t. So we get a negative e to the negative 1. Let's evaluate at the upper limit. Subtract negative e to the negative. Now t equals minus 1. So simplify, we'll have a negative 1 over e. Minus minus become plus. Minus minus become plus e. So normally we like to write the positive term up front. So get a e minus 1 over e. Now we can leave like this. Okay, we can leave like this. We don't need to really approximate unless it's a live application. So it's a similar the properties, definite integrals. If it's the integral is a summation of two functions, we can split into two integrals. The difference we can also split. But if the scalar inside the integration, we can pull out outside. Let's see this example. So we want to evaluate this one, and this one. Okay. So both of them from 1 to 3. So the upper limit and the lower limit are the same. So which means we can put them together. So we have 6x minus 18x cubed. Now this is a minus 2 times x 2x, then negative 2, then 2 times negative become plus 2x cubed, right? Then dx. So also from 1 to 3. Then we can combine like terms. So that's 4x. Then these two, that's negative 16x cubed. You still evaluate. Now we anti-differentiate. So we have 4x squared divided by 2 minus 16x raised by 4 divided by 4. Then we want to evaluate at 3, at 1. So this is simplified to be 2x squared minus 4x raised by 4. Evaluate at 1, at 3. So we evaluate at 3 first. 2 times 3 squared minus 4 times 3 raised by 4 minus now 2 times 1 squared minus 4 times 1 raised by 4. So 3 squared is 9, 2 times 9, 18. 3 raised by 4, 3 squared is 9, 9 times 9, 81. Well, 81 times 4, 243, right? 81 times 4, no, this is wrong. Times 3, so like that. So 81 times 4. So that's 4, so that's 324. Then minus 2, minus become plus 4. So we have 18 plus 4, 22, minus 324, minus 2. So 22 minus 2, that's 20. 20 minus 324, that's a negative 304. It's very easy to make mistake during the calculations. You can use your calculator, all right? So let's check. So what did I do? So I combine those two. Of course, we can do, individually. We can do individually, right? We can calculate this. We can calculate this, then subtract them. Or we can combine them. We can combine the like terms because the lower limit and the upper limits are the same. So I can combine them. Then anti-differentiate, then evaluate, then subtract. So a couple of steps involved. Yes, it's a negative 304. Let's see this example. Well, given this one equals 8. If you want to picture, you picture, we don't really know f, right? From 0 to 6, that's the area. So this area equals 8. From 5 to 6, or 5, let me use different color. 5 maybe here. Right, that's the area of this. The area, oh, actually it's much bigger. Actually, probably the picture looks like this. So this is a 6, this is a 0. And from 5 to 6, it's a 7. And the rest is only 1, right? Because total is 8. From 0 to 6, the whole area. So this is just 1. And we want to find 0 to 5. Well, we found already, right? This is a minus 7. So a minus 7. Well, let's put it into this. Then equals to 0 to 6, f of x dx, minus 5 to 6, f of x dx. Right, from 5 to 6. Right, so we want to find, so this one minus that one. So we can split this, the first one, into 0 to 5, f of x dx, plus 5 to 6, f of x dx. Then minus this one. Right? So this is this. From 0 to 6, the area of this whole thing. From 0 to 6. Then from 5 to 6 is this area of this. So we want to find the area of this. So just subtract them, which is a minus 7, which is 1. Let's see this example. So we want to evaluate the integral from 0 to 2 of this function. Right, 0 is here, 2 is here. We see this is a triangle. And this is a triangle, but this one is not. Right? The left-hand side is not. So what do? We can set up an integral. We set up an integral from 0 to 1. Now the function is x squared, right? So this is the function. We want to find the area underneath formed with the x-axis. So we can integrate x squared, so dx. Then this side of area is equals to the bottom triangle. Right? Area of triangle equals the bottom 2 minus 1 times the height. The height we can count. The height is about 1 point something. Right? Or we can integrate as well. Well, let's do integration actually. Let's not use algebra. Because we know how to integrate. So this area, we're going to set up integral as well from 1 to 2. Lower limit is 1, upper limit is 2. What's the function? The integral should be 2 minus x dx. Right? So we can calculate each one. So this one, we get x anti-differentiate. Then we evaluate at 0 and 1. So we just get 1/3. So the area of this piece is 1/3. Now we want to find the area of this triangle. So anti-differentiate, we get 2x minus x squared divided by 2. Evaluate at 1 and 2. So 2 times 2 minus 2 squared divided by 2. Then minus 2 times 1 minus 1 squared divided by 2. 2 times 2, 4. Minus 2 squared, 4 divided by 2, 2. Minus 2 times 1, 2. Minus become plus. 12 divided by 2. No, 1 squared. This is not 12. 1 squared, 1 divided by 2 is a half. So 4 minus 2 is 0. So the area under this is just half. So now you can see what is the one function, why we need a calculus, why we want to integrate. So how would we find the area of such, right? If we have a shape like this, how would we find the area of such thing? Because this is a curved. This is not straight. Right? The algebra won't help us because it's not a triangle. It's not a triangle. So that's why we can use this, can use integration to find the area of this. Oh, I forgot to add those two, right? Because I get a 1/3. So this one is 1/3. We find the area of this is 1/3. This is a half. We need to add those two. Right? We need a common denominators. When we add, you can use a calculator. I multiply by 2 over 2. I multiply by 3 over 3. Because I multiply by 1, the value won't change. So once I have a common denominator of 6, I can do 2 plus 3, the numerator. I can add the numerators. I get 5 over 6. So the definite integral as a net of change of function, right, from here. Let's see this example. The velocity, again, once we see velocity, we know there's a derivative of the position function. At time t seconds, an object moving in a straight line is given as linear function. So we know the position function has to be a quadratic, right? Actually, we could just anti-differentiate the velocity function to find that. And find the displacement of the object during the time from 1 to 3. So what do? We anti-differentiate this, right? Which we want to anti-differentiate 4t minus 1, then we evaluate at 1, at 3. So this is dt, the variable is t now. So we'll anti-differentiate first. So 4t squared divided by 2 minus t, or which is 2t squared minus t. So we evaluate at 3. Then minus we evaluate at 1. Well, 2 times 9, 18, minus 3, minus 2, plus 1. So 19 minus 5, 14. So we use the definite integrals to find the change between 2 points. Okay, marginal revenue. We use this for marginal revenue as also. A company's marginal revenue function is as such, right? You can see this is polynomial degree 2. So we know the revenue function has to be polynomial degree 3. So X denotes the number of units produced in one day. We want to determine the net change in revenue if X from 20 to 25. So what do we want to do? We want to set up integral from 20 to 25. And we want to anti-differentiate this function, the marginal function. Evaluate at 20 and 25, subtract them. We set up integrals like this. Then we anti-differentiate. So we get 0.03 x cubed divided by 3 minus 2x squared divided by 2 plus 25x. Then we want to evaluate at 20 at 25. So this two get 0.01 x cubed minus x squared plus 25x, right? Polynomial degree 3. Then we evaluate at those two values. So we better use a calculator for this. 0.01 times 25 raised by 3 minus 25 squared plus 25 times 25. Then minus 0.01 times 20 raised by 3 minus 20 squared plus 25 times 20. Okay. So it's just a calculation. Calculation is right here. So in the end, we should get negative 23.75. So decreased by negative. Okay, that's chapter 6, section 2, talking about the definite integral. So we have lower limit, we have upper limit to evaluate the integration. So we get a number. And for each one, we get a number. Compared to indefinite integrals, we get a family of functions. We always have to add a c.